Okay, now let's try and make things a little bit more interesting by considering function vector spaces. And in particular, we will try to approximate elements of L2 of -1, 1, the space of square integrable functions over the interval -1, 1, with elements of a very particular subspace called Pn of -1, 1, which is the space of polynomials of degree N -1 over the interval. A generic element of this subspace will have the following form, just a polynomial of degree N -1. And you can see that, like all polynomials, this is a linear combination of increasing powers of the variable t. So a self-evident naive basis, if you want, for this space is the set of all powers of t up to degree N -1. However, the naive basis is not orthonormal. It's clear that we can express any polynomial as a linear combination of vectors sk, but these vectors are not orthogonal nor unit norm. To make things more concrete, let's choose a candidate vector for approximation, and we will choose x equal to sine of t over the interval -1, 1. And we will try to approximate it with a second degree polynomial, so with an element of the subspace P3 of -1, 1. Clearly, second degree polynomials are square integrable functions over the interval, so this is a legitimate subspace. The way we're going to perform this approximation is first try to build an orthonormal basis for P3 of -1, 1. Because once we have an orthonormal basis, the best approximation will be simply the orthogonal projection of sine of t over this basis. And to project x over this basis, all we will need to do is take the inner product between sine of t and the elements of the basis. We will then compute the approximation error and compare that to what is probably the most common approximation of the sine function over an interval, which is Taylor approximation. The Taylor approximation is well known and easy to compute, but we will show that it is not optimal in the mean square error sense. Okay, so the first step is to build an orthonormal basis for Pn of -1, 1. We will use the Gram-Schmidt orthonormalization procedure, start with naive basis, and arrive at an orthonormal set. The Gram-Schmidt algorithm is an iterative procedure that takes one vector at a time from the original set and incrementally produces an orthonormal set. Each step has two substeps. The first is to take the next vector in line, say s of k, and remove from it all components that are collinear, namely in the same direction as all the other vectors that you have produced so far for the orthonormal set. And then, once you have whittled away all the components that are dependent to the previous vectors, you normalize the vector and obtain a new member of the orthonormal set. Let's look at it graphically for a very simple example. Suppose you have two vectors on the plane, which do form a basis because they're pointed in different directions, but they do not form an orthonormal basis. So the first step takes the first vector. Since it's the first vector, you don't have any other vector that you have computed so far. All you need to perform is the second substep of the procedure, just normalize the length to 1. And so the intermediate vector is identical to the original vector, and the final vector that you put in the bucket of orthonormal vector will be the rescaled version of S0 normalized to unit norm. Then you take the second vector, and you can see that S1 and U0 are not orthogonal, so they have some directionality in common. The idea is to remove from S1 all components that could be captured by U0. So in order to do so, you project S1 over U0, and this is the orthogonal projection of S1 over U0, okay, this orange vector, and then you remove it from S1. So you take away the part that could have been captured by the other vector. And if you subtract this orthogonal projection from S1, you obtain P1, which is now, of course, orthogonal to U0. The only thing that's left to do is to normalize P1 to unit norm, and here you have converted S1 and S0 to two orthonormal vectors. If we now apply the orthonormalization procedure to the naive basis for P3 of -1, 1, the only things that we have to adapt in our computations, well, first of all, remember the basis is 1, t squared, t cubed, and so on. And the inner product between two vectors in L2 of minus 1, 1 is defined as the integral from minus 1 to 1 of x of t, y of t in dt. Right? So with this in mind, let's start with the orthonormalization procedure. The first vector in the bucket of non-orthogonal vector will be this guy, 1. So S0 is equal to 1. The intermediate vector, because there are no vectors computed so far in the bucket of orthonormal vectors, will be equal to S0. The norm is the integral of 1 between minus 1 and 1 equal to 2, and therefore the first orthonormal vector in our basis will be the original vector normalized by the norm, which is square root of 2. So u0 will be square root of 1 over 2. Second vector in the bucket of non-normalized vector will be t, so the polynomial of degree 1. We take the inner product between this guy and the vector that we have computed before. Remember, that is square root of 1/2. So the inner product between these two vectors is simply the integral between minus 1 and 1 of t divided by square root of 2. Well, t is an antisymmetric function over the interval, so the integral between minus 1 and 1 will be equal to 0. What that means is that u0 and s1 are already orthogonal. p1 therefore will be equal to s1. We now compute the norm. It's easy to show that it's equal to 2/3, and therefore the second orthonormal vector in our bucket will be equal to square root of 3 over 2 times t. Third vector that we want to normalize is t squared. We take now the inner product between u0 and t squared. This time the inner product is not 0, it's actually 2 over 3 square root of 2, so there is a directionality in common. We take the inner product between t squared and u1 that we just computed the previous step. Again, an antisymmetric function, so the integral over a symmetric interval will be 0. Finally, p2, this intermediate vector, will be equal to s2 minus the component that has in common with u0. So, in this case, minus 1/3. We normalize this by computing the norm, and we find that u2 is equal to square root of 5 over 8 times 3t squared minus 1. So as you can see, the procedure is a little bit laborious and not particularly interesting, but what we do get in the end is a set of orthonormal polynomials for the interval minus 1, 1. These polynomials are known as the Legendre polynomials, and of course you can compute the Legendre polynomials of arbitrary degree. Here we're going to show the first 5, so degree 0 is the first basis vector, degree 1, and degree 2. This is what we're going to use in the approximation example that follows. But if you're interested, this is the third degree Legendre polynomial, the fourth degree, and the fifth degree, and so on and so forth. So back to our approximation problem, we're trying to approximate sine of t over the subspace P3 of minus 1, 1. We know that the best approximation is going to be given by the orthogonal projection of sine of t over the set of Legendre polynomials up to degree 2. So we compute these expansion coefficients as the inner product between the Legendre polynomials and the function that we want to approximate. So let's begin. Alpha 0 is the inner product between the first Legendre polynomial and sine of t. The first Legendre polynomial is just a constant, so we're taking the integral between minus 1 and 1 of sine of t which times a constant, which is equal to 0 because sine of t is antisymmetric. The first coefficient, alpha 1, is now the integral of square root of 3 over 2 times t times sine of t between minus 1 and 1, and it's equal to approximately 0.7377. The last coefficient is the inner product between the second degree Legendre polynomial and sine of t. Now, we could compute this, but it's enough to see that we're computing the integral of the product between an antisymmetric function and a symmetric function. Remember, it's the second degree Legendre polynomial is a parable like this. So the product will be an antisymmetric function, and the integral over a symmetric interval will be equal to 0. So finally, the orthogonal projection of sine of t over P3 of minus 1, 1 consists of only one term, alpha 1 times u of 1. And if you go back to the definition of y1, you can see this is equal to 0.9035t. This is similar, but not quite identical to the standard approximation for the sine around 0 given by Taylor's series, which is sine of t approximately equal to t. So in both cases, we're approximating the sine with a straight line, but the slope is a bit different. Let's see how this affects the approximation result. If we plot the sine, the Taylor approximation, and the orthogonal projection approximation, we don't really see a lot of difference, but we can concentrate on the error between the original function and the approximants. And so here you can see what happens. In red, we have the error of the Taylor series approximation, and we can see that the error is very small in an interval around 0, but then tends to grow large as we move away from 0. This is because the Taylor approximation is a local approximation. The orthogonal projection, on the other hand, minimizes the global distance, the mean square error between the approximation and the original vector. And so, although the error is not as small around the origin, the energy of the error is lower considered over the entire interval. It's a global optimization of the approximation. We can compute the distance between the sine function and the approximant. In the case of the Legendre approximation for the sine, we have that the mean square error of the approximation, the norm of the error, is 0.0337, whereas in the case of Taylor series, we have that it's 0.0857. So we have a factor of approximately 2.5 between the two mean square errors.